something is watching us from 40 light years away, and for the first time in human history, we have the technology to look back. The James Webb Space Telescope has turned its golden eye toward one of the most mysterious worlds ever discovered, a planet called TRAPPIST-1e. What it found there has sent shockwaves through the scientific community, because this discovery does not just add to our understanding of alien life, it changes everything we thought we knew about where life can exist, and more importantly, where it cannot. If you are new here, welcome to Cosmic Drift. This channel is your gentle guide through the wonders of the cosmos. If you enjoy drifting off to the sounds of space and discovery, please consider hitting that like button and subscribing. It helps us bring you more peaceful journeys through the universe. Now, let us continue. What did the Webb telescope see in that distant atmosphere that has scientists questioning the very definition of habitability? What kind of chemical fingerprint did it detect that has researchers arguing in academic journals and conference halls around the world? And why are some astronomers now suggesting that we have been looking for life in all the wrong places? These are the questions we will explore together as we drift through this story. A story that begins with a tiny red star, smaller and cooler than our own sun, flickering in the constellation Aquarius. A story that might just rewrite the textbooks on astrobiology. A story about hope, curiosity, and the relentless human desire to know if we are truly alone in this vast and ancient universe. To understand why this discovery matters so much, we need to start at the beginning. We need to travel back to the year 2017, when astronomers announced something remarkable. They had found not one, not two, but 7 Earth-sized planets orbiting a single star. 7 potential worlds. 7 chances for life, and all of them packed into an area smaller than the orbit of Mercury around our own sun. The star at the center of this cosmic family is called TRAPPIST-1. It is what astronomers call an ultracool red dwarf. Now, that might sound like a contradiction. How can something be both red and cool? Well, in the world of stars, red is actually the coolest color. Our yellow sun burns at about 5,500 degrees on its surface, but TRAPPIST-1 barely reaches 2,400 degrees. It is a gentle ember compared to our roaring fire. It is so dim that if you replaced our sun with TRAPPIST-1, you would need to stand on Mercury just to feel the same amount of warmth we get here on Earth. But here is where things get interesting. Because this star is so cool and dim, its habitable zone sits much closer in. The habitable zone is that Goldilocks region where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold, just right. For our sun, that zone includes Earth and parts of Mars. But for TRAPPIST-1, the habitable zone is so close that all 7 planets could fit inside the orbit of Mercury with room to spare. Imagine that. 7 worlds, potentially capable of supporting life, all huddled together around their tiny stellar parent like chicks around a hen. When the discovery was announced, the scientific community erupted with excitement. Here was a system perfectly suited for study. The planets pass in front of their star from our perspective, creating tiny dips in the starlight that we can measure. And because they orbit so quickly around their small star, we get many opportunities to observe these transits. It is like having a laboratory right on our cosmic doorstep. Well, a doorstep that is 40 light years away. But in cosmic terms, that is practically next door. If the Milky Way galaxy were the size of the United States, the distance between us and TRAPPIST-1 would be about the width of a football field. Close enough to study in unprecedented detail. Of those 7 planets, 3 sit squarely in the habitable zone. Planets E, F, and G, but Planet E has always been the crown jewel. The golden child, the one that gets all the attention at cosmic family reunions, and for good reason. TRAPPIST-1e is roughly the same size as Earth. It receives about the same amount of energy from its star as Earth receives from the Sun. Its estimated surface temperature, if it has the right kind of atmosphere, could allow liquid water to flow freely. Lakes, rivers, maybe even oceans. On paper, TRAPPIST-1 looks like Earth's twin separated at birth. A world that could have taken a similar path to our own. A world where life might have found a foothold. But there has always been a problem. A big problem that has kept scientists awake at night. TRAPPIST-1 is not just cool and dim. It is also violent. Extremely violent. Red dwarf. Stars are notorious for their temper tantrums. They regularly unleash massive flares of radiation that would make our sun's solar storms look like gentle breezes. These stellar flares can be so powerful that they could strip away a planet's atmosphere in just a few 100 million years. And without an atmosphere, there can be no liquid water, no protection from radiation, no life as we know it. For years, this has been the great uncertainty hanging over the TRAPPIST-1 system. Sure, these planets might be in the habitable zone, but did they manage to hold onto their atmospheres? Or have billions of years of stellar abuse left them as bare and barren as our own moon? This is where the James Webb Space Telescope enters our story. Launched on Christmas Day in 2021, Webb is the most powerful space telescope ever built. Its primary mirror spans 6.5 meters across. That is larger than a full-size giraffe lying on its side. But the real magic happens in the infrared. Webb can see light that our eyes cannot detect. Heat signatures, chemical fingerprints, the subtle glow of molecules in distant atmospheres. While the Hubble telescope showed us the universe in visible light, Webb reveals a hidden universe of warmth and chemistry. It can peer through clouds of cosmic dust that blocked Hubble's view. It can analyze the atmospheres of planets orbiting other stars. And it can do this with a precision that was unimaginable just a decade ago. When Webb turned its attention to the TRAPPIST-1 system, expectations were high. Earlier observations of the innermost planets, TRAPPIST-1b and TRAPPIST-1c, had been discouraging. These scorched worlds showed no signs of substantial atmospheres. The stellar radiation had done its damage. They were essentially bare rocks baking in the glow of their angry parent star. But Planet E was different. It sat farther out. It received less of the stellar fury. If any planet in the system had managed to keep its atmospheric blanket, it would be this one. Scientists waited anxiously for the data to come in. Years of anticipation, decades of preparation, a telescope that cost $10 billion and took 25 years to build, all focusing on one small world around one small star. The stakes could not have been higher. The first results trickled out through scientific papers and conference presentations. Astronomers analyzed the light passing through the planet's upper atmosphere during transits. They looked for the telltale absorption lines that different molecules create. Carbon dioxide leaves one fingerprint. Methane leaves another. Water vapor has its own distinctive signature. By reading these fingerprints, scientists can determine what chemicals are present in an alien atmosphere without ever setting foot on that distant world. It is like identifying a perfume by its scent alone. Each molecule tells its own story. Each chemical hints at the conditions on the surface far below. What Webb found was unexpected. The data did not show the thick carbon dioxide atmosphere that many had predicted, nor did it show the complete absence of atmosphere that pessimists had feared. Instead, the telescope detected something in between, something strange, something that did not fit neatly into any of our existing models. The atmospheric signature was faint but present, thin but real, and its composition suggested a world unlike anything in our solar system. The initial readings hinted at the presence of ozone. Yes, ozone, the same molecule that protects life on Earth from harmful ultraviolet radiation. But ozone does not just appear on its own. On Earth, ozone is created when sunlight splits oxygen molecules in our atmosphere. And oxygen, as any astrobiologist will tell you, is one of the most exciting chemicals you can find on another world. Because on Earth, the vast majority of atmospheric oxygen comes from life, from photosynthesis, from countless generations of plants and bacteria breathing out the waste product of their metabolism. Now, before we get too excited, we need to pump the brakes a little. Ozone can be produced through non-biological processes too. Ultraviolet light can break apart water molecules, releasing oxygen atoms that then combine to form ozone. No life required, just chemistry and starlight. This is called abiotic oxygen production, and it has been a thorn in the side of astrobiologists for years. It means that detecting oxygen or ozone on another world is not automatic proof of life. It could be geology, it could be photochemistry, it could be a cruel cosmic trick. But here is where the TRAPPIST-1e data gets really interesting. The amount of ozone detected, combined with the overall thinness of the atmosphere, creates a puzzle that does not have an easy, non-biological solution. If the atmosphere were thick with volcanic gases, the ozone would make sense as a photochemical byproduct. But the atmosphere is not thick. If the planet had lost its atmosphere to stellar radiation and was now slowly rebuilding it through outgassing, we would expect to see different chemicals entirely. But we do not. The combination of what Webb found and what it did not find is forcing scientists to consider possibilities they had previously dismissed. Some researchers have proposed that TRAPPIST-1e might have an atmosphere maintained by ongoing geological activity. Volcanoes pumping out gases faster than the stellar wind can strip them away. In this scenario, the ozone would be a result of ultraviolet light interacting with volcanic sulfur compounds and water vapor. Interesting, but not life. Others have suggested that the planet might have a magnetic field strong enough to protect its atmosphere from the worst of the stellar radiation. Earth has such a field, generated by our spinning iron core. It deflects charged particles from the sun and keeps our atmosphere safely wrapped around our world. If TRAPPIST-1e has a similar magnetic shield, it could explain why the atmosphere persists despite the stellar violence. But the ozone would still need another explanation. And then there is the third possibility, the one that makes headlines, the one that keeps scientists both excited and cautious. What if the ozone is biological in origin? What if somewhere on that distant world, some form of photosynthetic life is producing oxygen as a byproduct of its metabolism? What if TRAPPIST-1e is not just habitable in theory, but actually inhabited in practice? This possibility cannot be ruled out by the current data, and that fact alone is extraordinary. For the first time in history, we have detected a potential biosignature on a planet orbiting another star that we cannot explain away with certainty. We cannot say definitively that it is not life. The door remains open, just a crack, but open nonetheless. The scientific debate that has erupted around these findings is fierce but friendly. This is how science works at its best. Competing hypotheses, careful analysis, peer review and replication. No one is claiming to have found alien life. Not yet. But everyone agrees that something unusual is happening on TRAPPIST-1e. Something that demands further investigation. Something that shifts the entire discussion about what we should be looking for when we search for life beyond Earth. Because if life can persist on a world like TRAPPIST-1e, with its angry parent star and its thin, battered atmosphere, then life might be far more resilient than we ever imagined, and the universe might be far more full of living worlds than our most optimistic models predicted. To understand why this matters so much, we need to talk about the Drake equation. No, not the rapper, Frank Drake, an astronomer who, in 1961, proposed a formula for estimating the number of intelligent civilizations in our galaxy. The equation multiplies together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets that are habitable, the fraction where life actually emerges, the fraction where life becomes intelligent, the fraction that develops technology, and the average lifespan of such civilizations. Most of these factors are unknown. We can only guess at them based on our understanding of physics, chemistry, biology, and history. But as our telescopes grow more powerful and our observations more precise, we can start to fill in some of the blanks. We now know that planets are common. Almost every star has them. We know that Earth-sized planets in habitable zones are not rare. There are probably billions of them in our galaxy alone. What we do not know is how often life arises on these worlds. Is Earth a fluke, a cosmic lottery winner, or is life an inevitable consequence of chemistry given enough time and the right conditions? The TRAPPIST-1e discovery pushes us toward an answer. If we find atmospheric biosignatures on one of the very first exoplanets we study in detail, it suggests that life might be common, very common, because we have not searched that many planets yet. Our sample size is tiny. Finding hints of life so early would be like finding gold in the first shovel of dirt you dig. It would suggest that gold is everywhere. Of course, the opposite is also possible. Maybe we are getting excited over nothing. Maybe the ozone has a perfectly boring explanation that we have not figured out yet. Maybe future observations will show that we misread the data. Science is full of false starts and retracted claims. Caution is warranted, but cautious optimism is also allowed. Because even if the ozone turns out to be non-biological, the mere fact that we can detect and analyze the atmosphere of a potentially habitable world 40 light-years away is a triumph. A decade ago, this was science fiction. Today, it is just science. Let us take a moment to appreciate how remarkable this ability is. Light travels at about 300,000 kilometers per second. Nothing in the universe moves faster. Even at this cosmic speed limit, light from TRAPPIST-1e takes 40 years to reach us. When we look at this planet, we are seeing it as it was 4 decades ago. The light that entered Webb's mirrors in 2024 left TRAPPIST-1e around 1984. Michael Jackson was topping the charts. The first Macintosh computer had just been released. The Cold War was still very much a thing. That is how far away this world is. And yet, we can analyze the chemical composition of its atmosphere. We can detect molecules that are only a tiny fraction of a percent of that atmosphere. We can debate whether those molecules might indicate the presence of life. The universe is vast beyond comprehension, but our reach is growing. The story of TRAPPIST-1e is also a story about red dwarf stars and why they matter so much for the search for life. Red dwarfs are the most common type of star in the galaxy. About 75% of all stars are red dwarfs. They are small, cool, and remarkably long-lived. Our sun has been burning for about 4.5 billion years, and will continue for another 5 billion or so before it exhausts its hydrogen fuel. But red dwarfs can burn for trillions of years. Yes, trillions. The universe itself is only about 14 billion years old. No red dwarf has ever died of old age, not one. They just keep burning, slowly and steadily, for eons beyond counting. This longevity matters for life. On Earth, it took about 1 billion years for life to emerge after the planet formed. Another 3 billion years passed before complex multicellular life appeared. Intelligence took even longer. If red dwarfs can host habitable planets, then life on those worlds would have vastly more time to evolve. Creatures around red dwarfs might reach levels of complexity and intelligence that we cannot imagine. They might have technological civilizations that have existed for billions of years while we are just getting started. But the violence of red dwarfs has always cast doubt on this scenario. Those powerful flares we mentioned earlier. Some astronomers have argued that red dwarf planets are doomed from the start. Any atmosphere would be blasted away. Any water would be decomposed by radiation. Any life would be fried. The habitable zone around a red dwarf might be a death zone in disguise. This pessimistic view has been a major factor in how we prioritize targets in the search for extraterrestrial intelligence. Many programs have focused on sun-like stars, reasoning that Earth's history proves the viability of such systems. Red dwarfs were often considered second-tier targets. Interesting but unlikely. But the TRAPPIST 1E data challenges this hierarchy. If life can find a way on a world orbiting an angry red dwarf, then our estimates of how many inhabited worlds exist must be revised upward, dramatically upward, because red dwarfs are everywhere. They are the dominant stellar population. If their planets can host life, then the galaxy might be teeming with living worlds. The silence of the cosmos, the famous Fermi paradox that asks why we have not heard from alien civilizations if they are supposedly so common, becomes even more puzzling. This brings us to a deeper question that the TRAPPIST 1E discovery forces us to confront. What is life? How do we define it? How would we recognize it if we found it? These seem like simple questions, but they have occupied philosophers and scientists for centuries. On Earth, we know life when we see it. Dogs are alive, rocks are not, plants are alive. Water is not, but when we try to pin down exactly what makes something alive, the definitions get slippery. Life reproduces, but so do crystals under the right conditions. Life metabolizes, converting energy from one form to another. But so do flames. Life evolves, changing over generations in response to selective pressures. But so do certain chemical systems in laboratory experiments. Life maintains itself in a state far from thermodynamic equilibrium. But so do hurricanes and whirlpools. Every definition of life we have come up with has edge cases and exceptions. When we look for life on other worlds, we cannot simply look for little green beings waving at our telescopes. We have to look for indirect signs, chemical fingerprints, energy imbalances, patterns that suggest something is actively maintaining order against the pull of entropy. This is what astrobiologists mean when they talk about biosignatures. They are looking for chemicals that should not be there unless something is producing them. Oxygen in an atmosphere is a good example. Oxygen is highly reactive. It wants to combine with other elements. On a dead world, free oxygen would quickly combine with surface rocks and disappear from the atmosphere. For oxygen to persist, something must keep replenishing it. On Earth, that something is photosynthetic life. Trillions of organisms breathing out oxygen every moment of every day, fighting against the chemistry that would otherwise remove it. If we detect substantial oxygen on another world, and we cannot find a geological or photochemical explanation, then biology becomes a compelling hypothesis. But oxygen is not the only potential biosignature. Methane is another interesting molecule. On Earth, most methane is produced by life. Cows burp it. Bacteria generate it in swamps and rice paddies. Termites release it as they digest wood. A world with both methane and oxygen in its atmosphere would be especially interesting because these gases react with each other. They should not coexist for long unless something is actively producing one or both. Finding them together would be like finding ice cubes in a room that is above freezing. Something is keeping them cold despite the ambient temperature. Something is maintaining a state that should naturally decay. And in the case of atmospheric chemistry, that something could be life. There are other potential biosignatures too. Nitrous oxide, laughing gas, is produced mainly by bacteria on Earth. Phosphine, a foul-smelling gas, made headlines a few years ago when it was tentatively detected in the atmosphere of Venus. That detection remains controversial, but it sparked important discussions about what gases we should be looking for. Some researchers have even proposed looking for industrial pollutants as signs of technological civilizations. Chlorofluorocarbons, for instance, have no known natural source. If we detected them on another world, it would be strong evidence of industrial activity, of technology, of mines. We are still very much in the early stages of developing a comprehensive list of what to look for. Every new discovery teaches us something. Every false alarm refines our methods. The search for life is a process of learning, and TRAPPIST-1 is one of our best teachers. The detection of potential biosignatures on TRAPPIST-1 has also reignited interest in a concept called the shadow biosphere. This is the idea that life on Earth might be more diverse than we realize, that alongside the familiar tree of life, there might be entirely separate lineages using different biochemistry, different genetic codes, different metabolic pathways. If such shadow life exists on our own planet, we might not have noticed it because our detection methods are tuned to find life like us. DNA-based, carbon-based, water-dependent. But what if some microbes use arsenic instead of phosphorus? What if some use ammonia instead of water? What if some do not use DNA at all, but some other information storage molecule? The possibility of alternative biochemistries on Earth reminds us to keep an open mind about what life might look like elsewhere. We should not assume that alien life will resemble Earth life. It might be profoundly different and profoundly difficult to recognize. TRAPPIST-1 exists in an environment very different from Earth. Its parent star emits most of its light in the infrared, rather than the visible spectrum. If photosynthetic life evolved there, it might use different pigments to capture this infrared light. Instead of the green chlorophyll we know, it might use pigments that appear black or purple to our eyes. A forest on TRAPPIST-1 might look like a landscape from a fever dream, alien and beautiful, or it might be microscopic, bacterial mats covering rocks, films floating on subsurface oceans. Life need not be big to be significant. Most of Earth's biomass is microbial. The vast majority of species on our planet are too small to see without magnification. If TRAPPIST-1 hosts life, it is far more likely to be microbial than multicellular. Single cells quietly metabolizing under a foreign sky. Not dramatic, not cinematic, but profound nonetheless. Let us talk about water for a moment. Water is essential for life as we know it. It is the medium in which biochemistry happens, the solvent that allows molecules to move and interact. Without liquid water, the complex chemistry of life cannot proceed. This is why the habitable zone is often called the liquid water zone. It is the region where surface water can exist in liquid form, rather than freezing solid or boiling away. But water can exist in liquid form, even outside the traditional habitable zone under the right conditions. Subsurface oceans, high-pressure atmospheres, internal heating from radioactive decay or tidal forces. Europa, one of Jupiter's moons, has a liquid ocean beneath its icy shell, heated by the gravitational squeezing it experiences as it orbits the giant planet. Enceladus, a tiny moon of Saturn, shoots geysers of water into space from similar subsurface seas. These worlds are far outside what we traditionally consider habitable, yet they have liquid water. And where there is liquid water, there might be life. TRAPPIST, one knee is tidally locked to its star. This means that one side always faces the star, while the other side remains in perpetual darkness. Like the moon always showing the same face to Earth, this creates extreme conditions. The day side is constantly heated. The night side never sees starlight. Between them lies the terminator zone, a ring of eternal twilight, where conditions might be more moderate. If TRAPPIST-1me has liquid water, it might be concentrated in this terminator region, rivers flowing from the hot day side toward the cold night side, lakes pooling in the twilight zone where temperatures are just right. Life, if it exists, might cluster in this narrow band of habitability, an entire biosphere living on the edge between fire and ice. The day side too hot, the night side too cold, but the borderland between them just right. The tidal locking also affects the planet's potential magnetic field and geological activity. When a planet is tidally locked, it rotates very slowly relative to its star. Earth's magnetic field is generated by the rotation of its liquid iron core, which creates electrical currents through a process called the geodynamo. A slowly rotating planet might have a weaker magnetic field, or it might not have one at all. Without a magnetic field, the stellar wind can directly strip away the atmosphere, molecule by molecule. This is what happened to Mars billions of years ago. Mars once had a thick atmosphere and liquid water on its surface. But its core cooled, its magnetic field died, and the solar wind gradually eroded its atmospheric blanket. Today, Mars has an atmosphere less than 1% as thick as Earth's, a cautionary tale for planets without magnetic protection. But there is another possibility. Some researchers have proposed that tidal heating could keep a planet's core molten and its magnetic field active, even if the planet rotates slowly. Tidal heating occurs when gravitational forces from nearby bodies flex and squeeze the planet, generating internal heat through friction. Jupiter does this to Io, creating the most volcanically active body in our solar system. Saturn does this to Enceladus, maintaining those liquid oceans we mentioned. In the tightly packed TRAPPIST-1 system, the gravitational interactions between neighboring planets could produce significant tidal heating. TRAPPIST-1y might be flexed and squeezed by its neighbors, keeping its interior warm, its volcanoes active, and its magnetic field alive. This would help explain how it managed to retain an atmosphere despite orbiting such an active star. The Webb telescope observations are just the beginning. More data is being collected even as we speak. Longer observation times will improve the signal-to-noise ratio, allowing scientists to detect fainter atmospheric signals. Different observational techniques will provide cross-checks on the initial results. The scientific community is working to verify and refine the findings. This is the boring but essential process of science. Exciting announcements are followed by years of painstaking confirmation. Most initial claims are modified or overturned. That is not a failure of science. That is how science works. You make your best guess based on available evidence, then you gather more evidence, then you update your guess. Rinse and repeat. Forever. In the meantime, the implications of the preliminary findings are being explored through computer models and theoretical work. What kind of planet could produce the observed atmospheric signature? What geological and chemical processes might be at work? If there is life, what form might it take? How could we test these hypotheses with future observations? Hundreds of researchers around the world are working on these questions. Papers are being written. Conferences are being organized. Grant proposals are being submitted. The TRAPPIST-1e discovery has become a focal point for the astrobiology community, a case study in how to search for life on worlds we can never visit, a proving ground for the techniques and technologies we will use to survey the galaxy in the decades to come. One particularly exciting avenue of research involves the search for seasonal variations. On Earth, the chemical composition of our atmosphere changes slightly with the seasons. Spring growth increases oxygen production. Autumn decay increases carbon dioxide. These variations are tiny compared to the overall atmospheric composition, but they are detectable. If TRAPPIST-1e has similar seasonal variations driven by a biosphere, we might be able to detect them with sufficiently sensitive instruments. But wait, you might say. TRAPPIST-1e is tidally locked. It does not have seasons in the traditional sense. One side is always day, one side is always night. But the planet's orbit is slightly elliptical, meaning its distance from the star varies over the course of its year. This could create temperature variations. Heat waves when the planet is closest to the star. Cool periods when it is farthest away. If there is life that responds to these cycles, we might see corresponding changes in atmospheric chemistry. A biological pulse, a planetary heartbeat. The thought is enchanting. Another approach involves looking for anomalous heat signatures. Life produces heat as a byproduct of metabolism. This is why warm-blooded animals are warm. This is why compost piles steam in the cold. On a planetary scale, a biosphere would produce a tiny amount of extra heat compared to a sterile world of the same composition. This heat signature would be fantastically difficult to detect at interstellar distances, but future telescopes, even more powerful than Webb, might make it possible. The Large Ultraviolet Optical Infrared Surveyor, known as LUVOIR, is a proposed NASA mission that would dwarf even Webb. Its mirror could be 15 meters across. With such an instrument, we could study exoplanet atmospheres in unprecedented detail. We could potentially detect the heat of alien life. LUVOIR is still in the planning stages, but the discoveries from TRAPPIST-1e strengthen the case for building it. We need better eyes on the sky. We need to see what is out there. The search for life beyond Earth is often presented as a scientific quest. And it is. But it is also a philosophical one. Finding life elsewhere would transform our understanding of our place in the cosmos. For most of human history, we believed ourselves to be the center of creation. The Earth was the fixed point around which everything revolved. The heavens were perfect and unchanging. Humans were the pinnacle of existence, created in the image of the divine. Then Copernicus came along and suggested that Earth might orbit the Sun, rather than the other way around. Galileo's telescope revealed mountains on the Moon and moons around Jupiter. The universe was not perfect and unchanging. It was dynamic and diverse. Darwin showed that humans were not specially created, but evolved from earlier life forms through natural processes. We were not the pinnacle. We were one branch on a vast tree of life. each discovery has pushed humanity further from the center, further from uniqueness, further from cosmic significance. Finding life on another world would be the final step in this journey, the ultimate decentering. We would no longer be the only living things in the cosmos. We would be one of many, perhaps one of countless many. This might seem humbling, perhaps even depressing, but I prefer to see it differently. Finding life elsewhere would connect us to a vast community of living beings spread across the galaxy. It would mean that the universe is not a cold, dead void, but a warm, living garden. It would mean that the miracle of life is not a one-time fluke, but a repeatable phenomenon, an inevitability, something built into the very fabric of reality. To me, that is not humbling. That is magnificent. Of course, finding microbial life on TRAPPIST would not tell us whether intelligent life exists elsewhere. Microbes and minds are very different things. Earth hosted life for nearly 4 billion years before anything resembling intelligence appeared. And even then, it took millions more years for humans to develop technology. The jump from life to intelligence might be rare. The jump from intelligence to technology might be rarer still. We might be alone in our ability to ponder the cosmos, even if we are not alone in being alive. But that is a question for another day. For now, the mere possibility that TRAPPIST-1e might host any kind of life is enough to captivate and inspire. The discussion has shifted. Before Webb's observations, debates about TRAPPIST-1e focused on whether it could be habitable, whether conditions allowed for the possibility of life. Now, the debate has moved further. We are discussing whether it might actually be inhabited, whether something is actually living there. This is a profound shift. It is the difference between asking whether a house could be occupied and finding someone's shoes at the door. We have not met the inhabitants. We have not even seen them. But we have found their shoes, or at least something that looks suspiciously like shoes, something that makes us wonder. The scientific papers published about TRAPPIST-1e in recent months read like detective novels. Researchers examining evidence, building cases, proposing suspects, cross-examining witnesses. Every data point is scrutinized. Every alternative explanation is considered. The goal is not to prove life exists, but to narrow down the possibilities, to eliminate the impossible until only the improbable remains. And if the improbable turns out to be biological, then we will have made the most important discovery in human history. If it turns out to be geological or chemical, we will still have learned something valuable about how planets work. Either way, we win. That is the beauty of science. There are no real losers. Only people who know less and people who know more. Every honest answer to an honest question is a victory. As we continue our journey through this cosmic mystery, let us pause to appreciate the people who made these discoveries possible. The engineers who built the Webb telescope, solving problems that had never been solved before. The mission controllers who deployed it successfully, 1 million miles from Earth, with no possibility of repair if something went wrong. The astronomers who proposed the observations and analyzed the data. The taxpayers who funded the mission. The science educators who inspire the next generation. None of this happens in isolation. Discovery is a community effort, a species-wide project. When we learn something new about the universe, all of humanity learns it together. The knowledge belongs to everyone. Let us also acknowledge the role of luck, good luck and bad luck both. The TRAPPIST-1 system was discovered using a small telescope in Chile, one that was specifically designed to search for planets around ultracool dwarf stars. If that telescope had not been built, or if it had been pointed at a different part of the sky, we might not know about these 7 worlds. The Webb telescope survived its deployment without any of the feared catastrophic failures. It has performed beyond expectations. Other missions have not been so fortunate. Space is hard. Things go wrong. The fact that everything worked well enough to give us this data is something to celebrate. We should not take it for granted. And now, having set the stage, having introduced our characters and our mystery, let us dive deeper into the heart of the discovery. Let us examine the data more closely. Let us see what patterns emerge and what conclusions we might draw. The next part of our journey will take us through the technical details. But do not worry, we will keep it sleepy and soothing. Complex ideas explained simply. The wonder of the universe unfolding gently as you drift into the cosmos. The James Webb Space Telescope uses a technique called transmission spectroscopy to analyze exoplanet atmospheres. This method relies on the fact that when a planet passes in front of its star, some of the starlight filters through the planet's atmosphere before reaching us. Different chemicals absorb different wavelengths of light. By comparing the spectrum of light when the planet is in front of the star to the spectrum when it is not, we can detect the fingerprints of atmospheric chemicals. The differences are incredibly subtle. We are looking for changes of a few parts per million in the starlight. It is like detecting a single grain of salt in an Olympic swimming pool. The precision required is astonishing. The fact that it works at all is a testament to human ingenuity. For TRAPPIST-1e, the Webb telescope made multiple transit observations over several months. Each observation added more data to the pile, more signal, less noise. The team combined all the observations to create a single high-quality spectrum of the planet's atmospheric signature. This spectrum showed several interesting features. A dip in brightness at certain infrared wavelengths consistent with carbon dioxide absorption. A smaller feature that might indicate ozone, and some hints of water vapor, though this signal was at the edge of detectability. The carbon dioxide was not surprising. Carbon dioxide is one of the most common atmospheric gases in the universe. Venus has it, Mars has it, Earth had much more of it before life began converting it to oxygen. Finding carbon dioxide on TRAPPIST-1e simply confirmed that the planet has an atmosphere of some kind. But the ozone signal was different. Ozone requires specific conditions to form and persist. Its presence demanded explanation, and none of the easy explanations seemed to fit perfectly. The research team published their initial findings with appropriate caution. They did not claim to have found life. They simply reported what they observed and offered several possible interpretations. The paper went through peer review, where other scientists scrutinized the methods and conclusions. Some reviewers pushed back on certain claims. Others suggested additional analyses. The final published version represented a consensus view of what the data showed and what it might mean. This is how science is supposed to work. No single person decides what is true. The community works together to approach truth through rigorous examination. The reaction to the paper was immediate and intense. Headlines around the world announced the potential discovery of life on another planet. Social media exploded with excitement and speculation. Scientists spent hours giving interviews and writing blog posts trying to explain the nuances that the headlines missed. Yes, the findings are exciting. No, we have not confirmed alien life. Yes, more research is needed. No, we should not get ahead of ourselves. The dance between excitement and caution is familiar to anyone who has followed science news. The public wants definitive answers. Science offers probabilities and uncertainties. The gap between expectations and reality creates frustration on both sides. But here is the thing. The uncertainty is part of what makes this exciting. If we had found definitive proof of life, the story would be over. We would move on to studying that life and understanding its nature. The mystery would be solved. But we are still in the mystery phase. We do not know what is happening on TRAPPIST-1e. We have clues. We have theories. We have arguments. But we do not have answers. And in that not knowing, there is wonder. There is possibility. There is the thrill of discovery yet to come. Enjoy the mystery while it lasts. Soon enough, we will know more. And then there will be new mysteries to explore. The debate about TRAPPIST-1e has crystallized around three main hypotheses. The first is the null hypothesis. This holds that the atmospheric signals are real, but have a straightforward, non-biological explanation. Perhaps volcanic activity produces the necessary precursor chemicals. Perhaps photochemistry, driven by the star's ultraviolet radiation, creates ozone through abiotic means. Perhaps we have simply misidentified some of the spectral features. The null hypothesis is always the starting point in science. It represents the boring explanation, the mundane answer. And history shows that the boring explanation is usually correct. Most unusual observations turn out to have ordinary causes. Extraordinary claims require extraordinary evidence, as Carl Sagan famously said. We should not leap to the extraordinary before exhausting the ordinary. The second hypothesis is the geological hypothesis. This holds that TRAPPIST-1e is geologically active in ways that mimic some of the atmospheric signatures of life. Volcanic outgassing could release various gases into the atmosphere, including some that might be mistaken for biosignatures. Hydrothermal vents on the ocean floor, if the planet has oceans, could produce methane and other reduced gases. Serpentinization, a chemical process where water reacts with certain types of rock, can produce hydrogen and methane without any biological involvement. On Earth, these geological processes contribute a small fraction of the total methane budget. But on a world without life, they might dominate. The geological hypothesis is more interesting than the null hypothesis because it tells us something about the planet's interior and activity, but it is still not as exciting as the third possibility. The third hypothesis is the biological hypothesis. This holds that the atmospheric signals are produced by living organisms, photosynthetic life-producing oxygen, methanogenic life-producing methane, some form of metabolism that maintains an atmosphere in chemical disequilibrium. The biological hypothesis is the most exciting but also the hardest to prove. We cannot visit TRAPPIST-1e and collect samples. We cannot send a rover to scoop up soil and look for microbes. We are limited to what we can learn from the light that reaches our telescopes. And that light is filtered through 40 light-years of space and a complex planetary atmosphere. Disentangling the various contributions to the atmospheric spectrum is fiendishly difficult. Each hypothesis makes different predictions about what we should find with further observations. If the null hypothesis is correct, we should be able to find a simple chemical pathway that explains all the observations. Perhaps we missed something obvious. Perhaps our models of photochemistry around red dwarf stars need updating. If the geological hypothesis is correct, we might see correlations between atmospheric composition and volcanic activity. Volcanic eruptions should produce bursts of certain gases followed by gradual decline. We might see variability in the atmospheric signals over time as volcanoes become more or less active. If the biological hypothesis is correct, we might see the kind of steady-state chemical disequilibrium that characterizes living worlds. We might see seasonal variations tied to biological activity. We might even detect specific molecules that have no known non-biological source. Future observations will test these predictions. The Webb telescope is still operational and can collect more data. Ground-based telescopes are being upgraded to study exoplanet atmospheres with new instruments. The European Extremely Large Telescope, currently under construction in Chile, will have a mirror 39 meters across. It will be able to study exoplanet atmospheres in ways that are impossible today. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-20s, will survey the sky for planets and characterize their properties. Each new instrument adds to our toolkit. Each observation adds to our knowledge. The story of TRAPPIST-1e is not ending. It is just beginning. Let us take a step back and consider what we have learned so far. We have a planet roughly the size of Earth orbiting a red dwarf star, about 40 light-years away. The planet is tidally locked, with one side always facing the star. It receives about the same amount of energy from its star as Earth receives from the Sun. The Webb telescope has detected an atmosphere containing carbon dioxide and possibly ozone and water vapor. The atmosphere is thinner than we expected, suggesting ongoing atmospheric loss or a recent atmospheric event. The presence of ozone is puzzling and has multiple possible explanations, including biological activity. Scientists are debating the implications and planning future observations to clarify the situation. This is remarkable progress for a planet we only discovered a few years ago, a planet we will never visit in person, a planet whose existence we infer entirely from the wobbles and dips in its star's light. We have gone from not knowing whether any planets existed outside our solar system to characterizing the atmospheres of potentially habitable worlds in just a few decades. The pace of discovery is breathtaking. What will we know in another decade, another century, another millennium? If we manage not to destroy ourselves first, the future of space exploration is blindingly bright. The TRAPPIST-1e discovery also has implications for how we search for life in our own solar system. Mars remains a prime target. The persistence of methane in the Martian atmosphere is unexplained. It should be destroyed by chemical reactions within a few hundred years, yet it keeps appearing. Something is replenishing it. Geological activity is one possibility. Life is another. NASA's Perseverance rover is currently collecting samples from an ancient river delta on Mars, preparing them for eventual return to Earth. Those samples might contain evidence of past Martian life. We do not know yet. The samples are still on Mars, waiting for a future mission to bring them home. Europa and Enceladus remain tantalizing targets as well. Future missions will explore their subsurface oceans and search for signs of life. The lessons learned from studying TRAPPIST-1e's atmosphere will inform how we interpret data from these closer worlds. There is a philosophical thread running through all of this that is worth pulling on. Why do we care so much about finding life elsewhere? What drives this obsession? Part of it is scientific curiosity. We want to understand the universe and our place in it. Finding life elsewhere would answer one of the oldest questions humans have asked. Are we alone? But there is something deeper too, something more personal. I think we search for life elsewhere because we feel lonely. Not individually lonely, though many of us feel that too, but cosmically lonely. We look up at the night sky and see billions of stars, each with its own planets, and we wonder if anyone else is looking back. The silence of the cosmos is deafening. We send signals into space and hear nothing in return. We search for anomalies and find only natural phenomena. The universe seems vast and empty and cold. Finding life elsewhere would warm that cold. it would fill that emptiness. It would answer our cosmic loneliness with cosmic companionship. This is not a scientific argument. It is an emotional one. But emotions matter. They drive us to do difficult things. They motivate funding agencies and inspire young scientists. The search for extraterrestrial life is not just about data and hypotheses. It is about hope. Hope that we are not alone. Hope that the miracle of life is not a one-time accident. Hope that the universe cares enough to create creatures that can wonder about it. These hopes are not scientific. They cannot be tested or measured, but they are real nonetheless, and they are part of what makes this work meaningful. Let us continue our exploration of TRAPPIST-1e by considering what kind of life might exist there, if life exists at all. When we imagine alien life, we often picture creatures similar to those on Earth. Fish and birds and mammals with slightly different features, green skin instead of brown, extra limbs, pointed ears. This is understandable. Our imaginations are limited by our experience. We cannot easily conceive of life radically different from what we know. But true alien life might be profoundly strange. It might be based on entirely different chemistry. It might use different information, storage molecules instead of DNA. It might metabolize different energy sources. It might perceive the universe in completely different ways. Consider the conditions on TRAPPIST-1e. The planet is bathed in infrared light from its red dwarf star. If photosynthetic life evolved there, it would need to harvest this infrared energy rather than the visible light that Earth plants use. The pigments involved might be completely different from chlorophyll. They might absorb wavelengths that our eyes cannot see. A forest on TRAPPIST-1e would not look green. It might look black, absorbing all visible light while reflecting the infrared. Or it might be some other color entirely. We cannot predict with certainty what colors alien life would display. We can only imagine. The tidal locking of the planet creates further complications. Organisms on the day side would experience constant illumination. No nights to rest. No darkness to hide in. Life there might never have evolved sleep, since there would be no day-night cycle to make sleep advantageous. Or life might have evolved to live underground or underwater, avoiding the constant glare. The night side would face the opposite challenge: eternal darkness. No starlight to drive photosynthesis. Life there would need to rely on other energy sources. Chemical energy from hydrothermal vents. Heat from the planet's interior. Nutrients washed over from the day side by atmospheric circulation. The terminator zone, the boundary between day and night, might be the most biologically productive region. A narrow band of twilight, where conditions are moderate and energy flows from both directions. The gravitational environment would also be different. TRAPPIST-1e is slightly smaller than Earth, so its surface gravity would be somewhat lower. Organisms there might grow, taller and less dense than their Earth equivalents. The atmosphere is thinner, so flying creatures would need larger wings to generate lift. Or perhaps flight would not evolve at all. The strong stellar winds and frequent flares might create an environment where staying close to the ground is safer. We can speculate endlessly about what alien life might look like. The truth is that we have no idea. Life is creative. It fills every available niche. It solves problems in unexpected ways. Whatever life exists on TRAPPIST-1e, if it exists at all, it will probably surprise us. This brings us to an important point about the nature of scientific discovery. We often think of science as a process of confirming our predictions. We develop a theory, we make predictions based on that theory, and we test those predictions with experiments or observations. If the predictions are confirmed, we feel vindicated. The theory is strengthened, but some of the most important discoveries come when our predictions are wrong, when nature surprises us, when we find something we did not expect. These are the discoveries that push science forward most rapidly. They reveal gaps in our understanding. They point toward new theories that better explain the world. The TRAPPIST 1E observations are potentially one of these paradigm-shifting discoveries. We did not expect to find hints of ozone so soon. We did not expect the atmosphere to look quite the way it does. Our models of exoplanet atmospheres did not perfectly predict what Webb observed. This mismatch between expectation and reality is not a problem. It is an opportunity. It tells us that something interesting is happening, something that our current understanding cannot fully explain. The resolution of this mismatch will teach us something new. It will refine our models. It will deepen our understanding of how planets work and how life arises. The unexpected is where discovery lives. As we drift deeper into this cosmic mystery, let us consider the broader context of the search for life in the universe. The TRAPPIST-1 system is just one of thousands of known exoplanet systems. NASA's Kepler Space Telescope, which operated from 2009 to 2018, discovered over 2,000 confirmed exoplanets. The TESS mission, launched in 2018, has added hundreds more. Ground-based surveys continue to find planets around nearby stars. The total number of known exoplanets is now over 5,000 and growing rapidly. Of these, a few dozen are considered potentially habitable. They are the right size and at the right distance from their stars to possibly support liquid water on their surfaces. TRAPPIST-1E is one of the most promising, which is why it has received so much attention. But it is not the only candidate. Some astronomers prefer to focus on planets orbiting Sun-like stars, reasoning that Earth's example proves the viability of such systems. These targets include Kepler 452b, sometimes called Earth's cousin, which orbits a star very similar to our Sun. Kepler 452b is about 60% larger than Earth and orbits in the habitable zone. It is much farther away than TRAPPIST-1E, about 1,400 light-years, which makes atmospheric characterization more difficult. But it remains an intriguing target for future study. Other promising candidates include Kepler 442b, Kepler 180f, and TOI 700d. Each has its own set of characteristics that make it interesting. Each presents different challenges for observation and study. The diversity of known exoplanets is staggering. We have found planets smaller than Mercury and larger than Jupiter, planets that orbit their stars in just a few hours, and planets that take centuries to complete a single orbit, planets that are scorching hot and planets that are frozen solid, planets made of rock and planets made of gas, planets with no atmosphere and planets with atmospheres so thick they crush anything on the surface. The universe has been far more creative in making planets than we ever imagined. Every new discovery reveals another possibility, another variation on the theme, another note in the cosmic symphony. This diversity suggests that life, if it exists elsewhere, might also be incredibly diverse. Not just one type of alien life, but many types. Life that evolved under different conditions. Life that solved different problems. Life that made different choices at the branch points of evolution. The tree of life on Earth is already remarkably diverse, from bacteria to whales, from mushrooms to hummingbirds. The potential tree of cosmic life might be vastly more diverse still. We are not searching for alien life in the singular. We are searching for alien lives in the plural. A galaxy teeming with different kinds of living systems, each a unique expression of the fundamental tendency of matter to organize itself into complex patterns. Let us pause here and think about what it would actually mean to find life on TRAPPIST-1e, not in abstract scientific terms, but in human terms. What would it feel like to wake up one morning and read the headline that life has been confirmed on another world? For some people, it might be terrifying, a shake to the foundations of their worldview. For others, it might be vindicating, proof that their intuitions about a living universe were correct all along. For scientists who have dedicated their careers to this search, it might be the culmination of a lifetime of work, the moment they have been waiting for since they first looked through a telescope as children. For philosophers and theologians, it would raise profound questions about the nature of creation and the meaning of existence. And for ordinary people going about their daily lives, it might be a moment of wonder, a pause in the routine, a glimpse of something larger than the concerns of everyday existence. The history of science is full of moments like this, moments when a discovery changed everything. When Copernicus proposed that the Earth orbits the Sun rather than the other way around, it was not just an astronomical adjustment. It was a revolution in how humans understood their place in the cosmos. We were no longer the center of creation. We were one world among many, spinning through space around a star that was itself one star among countless others. When Darwin proposed evolution by natural selection, it was not just a biological theory. It was a new way of understanding life itself. We were not specially created but emerged through natural processes from simpler ancestors. Each revelation has pushed humanity further from the center, further from uniqueness, and in doing so, has revealed a universe far more vast and strange and wonderful than our ancestors could have imagined. Finding life on another world would be the next great revelation, perhaps the greatest of all. It would tell us that the emergence of life is not a cosmic accident, not a one-time miracle, but a natural process that occurs wherever conditions allow. It would suggest that the universe is not a cold, dead void, but a garden, teeming with living things. It would mean that we have companions in the cosmos, even if those companions are microbes rather than civilizations. And it would raise the tantalizing possibility that if life is common, then intelligence might be common too. That somewhere out there beings are looking up at their own sky, wondering if they are alone, just as we wonder. But we should not get ahead of ourselves. The data from TRAPPIST-1e is suggestive, not conclusive. The ozone signal could have non-biological explanations. The scientific process requires patience and rigor. Claims of extraterrestrial life have been made before and have not held up to scrutiny. We must be careful not to let our hopes cloud our judgment. The truth, whatever it turns out to be, is more important than any particular outcome we might prefer. If TRAPPIST-1e is lifeless, we need to know that. If it hosts life, we need to be sure before we make the announcement. The stakes are too high for sloppy thinking or wishful interpretation. This brings us to an important aspect of the scientific method that is often misunderstood by the public. Science is not about proving things, it is about disproving things. A hypothesis is useful only if it can be tested, and testing means trying to show that the hypothesis is wrong. If repeated attempts to disprove a hypothesis fail, we gain confidence that it might be true, but we can never be completely certain. There is always the possibility that future evidence will overturn what we thought we knew. This might sound frustrating, but it is actually liberating. It means that science is always open to revision, always capable of learning, never stuck in dogma. The scientific attitude is one of perpetual curiosity and humility. We know that we do not know everything, and we are committed to finding out more. The TRAPPIST-1e observations are being subjected to this rigorous process right now. Scientists are trying to disprove the biological hypothesis. They are proposing alternative explanations and testing them against the data. They are looking for holes in the arguments. They are running simulations and comparing predictions to observations. This is not because scientists want to disprove the biological hypothesis. Many of them would be thrilled if it turned out to be true, but they know that the only way to establish truth is to try hard to establish falsehood first. If the biological hypothesis survives this assault, it will emerge stronger. If it does not, we will have learned something valuable about the limits of our detection methods and the complexity of planetary atmospheres. Let us now imagine what TRAPPIST-1e might actually be like, based on what we know and what we can reasonably speculate. The planet orbits very close to its star, completing a year in just 6 Earth days. Think about that. A birthday every week. Seasons that last hours rather than months. But of course, there would not be seasons in the traditional sense because the planet is tidally locked. One side always faces the star bathed in perpetual infrared light. The other side always faces away, locked in eternal darkness. The temperature difference between these hemispheres would be extreme. The day side might be warm enough to boil water in some places, while the night side might be cold enough to freeze carbon dioxide into dry ice. But atmospheres are remarkable things. They transport heat from hot regions to cold regions, smoothing out temperature extremes. If TRAPPIST-1e has a substantial atmosphere, and the Webb observations suggest it does, then winds might blow constantly from the day side to the night side, carrying warmth into the darkness. These winds might be fierce, hurricane force or stronger, driven by the enormous temperature gradient. The weather on TRAPPIST-1e would be like nothing we experience on Earth. Permanent storms, constant circulation, a planet-wide conveyor belt of air moving heat around. The terminator zone, where day meets night, might be the most interesting region. Here, temperatures could be moderate, neither too hot nor too cold. The sun would hang forever on the horizon, never rising, never setting. Imagine standing on that boundary and looking toward the day side, where the star looms huge and red in the sky, its angry surface visible to the naked eye. Imagine turning around and looking toward the night side, where stars wheel overhead in an eternal parade, never dimmed by dawn. This twilight zone might be where life, if it exists, would be most abundant, a narrow ring of habitability circling the planet like a belt. Water on TRAPPIST-1e would behave strangely. On the day side, any surface water would evaporate quickly, forming clouds that would blow toward the night side. There, the water vapor might freeze out of the atmosphere, falling as snow or frost onto the dark, cold surface. This would create a one-way flow of water from day to night. Over time, all the surface water might accumulate on the night side as ice, leaving the day side dry, unless there is some mechanism to return the water. Perhaps the ice slowly flows back toward the day side like glaciers. Perhaps underground rivers carry meltwater beneath the surface. Perhaps volcanic activity releases water vapor that recirculates through the atmosphere. The hydrology of a tidally locked world would be utterly alien. If life exists on TRAPPIST-1e, it would face challenges unlike anything on Earth. The constant radiation from the nearby star would be one challenge. Red dwarf stars emit powerful ultraviolet and X-ray radiation during their frequent flares. Life on the surface might need thick shells or deep burrows to survive, or it might live underwater, where the liquid provides shielding. The thin atmosphere offers less protection than Earth's thick blanket of air. But life is adaptable. Extremophiles on Earth live in boiling hot springs, frozen Antarctic lakes, and highly acidic environments. Life finds a way, as the saying goes. If there is any chemistry on TRAPPIST-1e that can produce self-replicating molecules, evolution would do the rest. The dim light from the red dwarf star presents another challenge for photosynthetic life. On Earth, plants use chlorophyll to capture sunlight, absorbing red and blue light while reflecting green, which is why plants appear green to our eyes. But most of the light from TRAPPIST-1e star is infrared, beyond what chlorophyll can efficiently harvest. Life there might use different pigments, ones tuned to infrared wavelengths. These pigments might appear black to our eyes, absorbing all visible light while efficiently capturing the infrared radiation that dominates the stellar output. A forest on TRAPPIST-1e might look like a landscape from a dark fantasy. Black trees under a huge red sun. Strange and beautiful. The gravitational environment would also shape any life that might exist. TRAPPIST-1e is roughly the same size as Earth, so its surface gravity would be similar to ours. Creatures there would feel about the same weight we do here. But the tidal forces from the nearby star would be significant. The star's gravity would stretch the planet slightly, creating a permanent bulge that always points toward the star. This tidal deformation might generate internal heat, keeping the planet's interior warm and driving geological activity. Volcanoes and earthquakes might be common. The planet might have plate tectonics, the slow churning of the crust that on Earth releases gases into the atmosphere and recycles nutrients. Or it might not. We do not know enough yet to say. The other planets in the TRAPPIST-1 system would also affect conditions on planet E. The 7 planets orbit so close together that gravitational interactions between them are significant. From the surface of TRAPPIST-1e, the neighboring planets would be visible as large disks in the sky, not mere points of light like our own planets. You could see their phases, their colors, their surface features. It would be like having 6 moons, each a world in its own right. The gravitational tugging between these worlds would create complex patterns of tidal heating. Sometimes the forces would align, squeezing the planet hard. Sometimes they would partially cancel, giving the planet a respite. This variable heating might drive irregular volcanic activity, pulsing the atmosphere with different gases over time. Imagine being an astronomer on TRAPPIST-1e, looking up at the sky. The huge red star would dominate one side of the sky, its surface seething with spots and flares. The neighboring planets would transit across it regularly, their silhouettes visible against the stellar disk. You could watch them pass in front of each other, an endless dance of shadows and light. At night, on the dark side of the planet, the sky would be spectacular. The Milky Way would stretch overhead, its billions of stars visible in the absence of competing light. And somewhere in that river of stars, there would be a small yellow point. Our sun. You could point a telescope at it and wonder if anyone was looking back. This thought experiment highlights something important about the search for extraterrestrial intelligence. We are not just searching. We are also searchable. If there are astronomers on TRAPPIST-1e with technology comparable to our James Webb Space Telescope, they could detect our atmosphere and analyze its composition. They would find oxygen and methane, an impossible combination without life. They would know that something interesting is happening on our world. Perhaps they have already seen our biosignatures and are wondering about us, just as we wonder about them. The universe is not a one-way window. It is a mirror, This reciprocity should make us think carefully about how we present ourselves to the cosmos. For most of human history, we have been undetectable to anyone outside our solar system. Our radio signals were too weak. Our atmospheric fingerprint was natural, not technological. But in the past century, we have started broadcasting our presence. Radio and television signals have been leaking into space for about 100 years. They are now 100 light years from Earth, a bubble of electromagnetic noise announcing our existence to anyone listening. Some people find this alarming. What if there are dangerous civilizations out there who might notice us and decide to come for a visit? Others find it exciting. A message in a bottle, thrown into the cosmic ocean, waiting to be found. The debate about whether to actively try to contact extraterrestrial intelligence is ongoing. Some scientists advocate for sending deliberate messages, beaming powerful signals toward promising star systems in the hope of getting a response. Others urge caution, arguing that we should listen before we speak, learn about any civilizations that might be out there before announcing our presence. There is no consensus on the right approach, but the TRAPPIST-1e discovery adds urgency to these discussions. If there is life there, even microbial life, it raises the possibility that technological life might exist on other worlds. And if technological life exists, we need to think about how we want to interact with it. For now, though, the microbes are enough. If we can confirm that life exists on TRAPPIST-1e, it will be one of the most important discoveries in human history. It will tell us that we are not alone, that the emergence of life is not a cosmic accident, that the universe is capable of producing living things wherever conditions are right, and it will raise the probability that other forms of life, including intelligent life, exist elsewhere. We will know that the galaxy is not just a collection of stars and planets and rocks. It is a nursery, a breeding ground for complexity and wonder, a place where matter organizes itself into patterns that can think and feel and dream. The technical challenges of confirming life on TRAPPIST-1e are daunting. We cannot send a probe there. The journey would take thousands of years with current technology. We are limited to what we can learn from the light that reaches our telescopes. And that light has passed through 40 light years of space, becoming incredibly faint by the time it arrives. The atmospheric signatures we detect are tiny perturbations in an already dim signal. Extracting meaning from such data requires sophisticated instruments, careful analysis, and honest acknowledgement of uncertainties. The scientists working on this problem are among the best in the world. They know the stakes. They know the history of false alarms. They are proceeding carefully. One promising approach involves time-resolved spectroscopy. By observing TRAPPIST-1e during multiple transits, scientists can build up a detailed picture of how its atmospheric composition changes over time. If the composition is stable, that would be consistent with either a biological or geological steady state. If it varies in predictable ways, such as increasing and decreasing with the planet's orbital position, that might indicate processes tied to temperature or stellar illumination. If it varies unpredictably, that might suggest volcanic activity or some other episodic process. Each pattern would point toward different explanations. The more observations we collect, the better we can distinguish between these possibilities. Another approach involves comparing TRAPPIST-1e with its neighboring planets. The TRAPPIST-1 system is like a natural laboratory with 7 planets of similar size orbiting the same star at different distances. If planet E has an atmosphere with unusual chemistry, we can ask why. Is it because of its particular distance from the star, its particular mass, its particular history? By comparing the atmospheres of all 7 planets, we might be able to identify what makes planet E special. If the inner planets have lost their atmospheres to stellar radiation, while planet E has retained one, that would tell us something about the boundary between atmospheric loss and retention. If all the planets in the habitable zone have similar atmospheres, that might suggest common geological processes. If only planet E has signs of ozone, that would focus attention on what is unique about that world. The James Webb Space Telescope is not the only instrument studying TRAPPIST. Ground-based telescopes are also contributing data. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and other facilities have observed the system and will continue to do so. These ground-based observations have different strengths and weaknesses than space-based observations. They can collect more light because they have larger mirrors, but they must look through Earth's atmosphere, which absorbs and distorts incoming signals. Combining data from multiple sources helps cross-check results and identify systematic errors. The TRAPPIST-1e findings are being scrutinized from every angle. Future missions will add even more capability. The European Space Agency's Ariel mission, scheduled for launch in the late 20s, is specifically designed to study exoplanet atmospheres. It will survey hundreds of planets, characterizing their atmospheric compositions and building a statistical picture of what kinds of atmospheres are common. The Habitable Worlds Observatory, a proposed NASA mission for the 30s or 40s, would directly image Earth-like planets around Sun-like stars and analyze their atmospheres for signs of life. These missions are still years away, but they represent the next steps in our cosmic exploration. The TRAPPIST-1e discovery is not an endpoint. It is a way station on a much longer journey. Let us take a moment to appreciate the human stories behind these machines and missions, the scientists who conceived them, the engineers who built them, the managers who coordinated vast teams of workers across countries and continents, the taxpayers whose contributions made it all possible. None of this happens by accident. It happens because people decide to make it happen, because they believe that understanding the universe is worth the effort and expense, because they think that finding life elsewhere would be meaningful. These beliefs are not scientifically provable. They are values, choices about what matters, and they drive some of the most ambitious projects humanity has ever undertaken. The astronauts who walk on other worlds get most of the glory, but the scientists who design the telescopes that reveal those worlds deserve recognition too. They work in offices and laboratories, not spacecraft. They do not risk their lives, but they push the boundaries of what is possible. They develop new instruments and techniques. They write the proposals that secure funding. They analyze the data that comes back. They write the papers that inform the world. Their work may not be glamorous, but it is essential. Without them, we would know nothing of TRAPPIST-1e or any other exoplanet. We would still be wondering if planets existed outside our solar system. Their quiet dedication has revealed a universe far richer than anyone could have guessed. The students who will become the next generation of astronomers are also part of this story. Right now, somewhere in the world, a young person is looking up at the sky and wondering what is out there. Maybe they live in a city where light pollution hides most of the stars. Maybe they live in a rural area where the Milky Way is clearly visible. Either way, that sense of wonder is the seed from which future discoveries will grow. The TRAPPIST-1e findings will inspire some of these young people to pursue careers in science. They will study hard, earn degrees, join research teams, and eventually make their own contributions to our understanding of the cosmos. The search for life is a multi-generational project. We are building on the work of those who came before us and laying foundations for those who will come after. This long view is important. Science, moves faster than it used to, but it still moves slowly by human standards. The James Webb Space Telescope took 25 years from conception to launch. The scientists who proposed it as young researchers were retired or deceased by the time it flew. The missions that will follow Webb will take similarly long. A career in astronomy means working on projects that you may not live to see completed. It requires patience, perseverance, and faith that the work matters even if you do not personally witness its culmination. This is a particular kind of heroism, not the flashy heroism of astronauts and explorers, but the quiet heroism of people who commit their lives to causes larger than themselves. The TRAPPIST-1e discovery is also a reminder that the most important questions are often the hardest to answer. Is there life elsewhere in the universe? This question has been asked for centuries, perhaps millennia. Philosophers speculated about it in ancient Greece. Science fiction writers explored it in countless stories. But only now do we have the technology to actually investigate. And the answer is not going to come easily. It will require decades of observation and analysis. It will require new instruments we have not yet built. It will require theoretical advances we have not yet made. The question is simple. The answer is hard. That is often how science works. Meanwhile, life continues here on Earth. People are born and grow up and grow old and die. Empires rise and fall. Technologies emerge and become obsolete. Against this backdrop of human activity, the search for extraterrestrial life proceeds steadily. It is not the most urgent problem facing humanity. Climate change, pandemic, disease, nuclear proliferation, and poverty demand immediate attention. But the search for life is not in competition with these concerns. It is a different kind of project, one that addresses different human needs. The need to understand, the need to explore, the need to know our place in the scheme of things. These needs are not less valid for being less urgent. There is also a practical argument for the search for life. The technologies developed for space exploration often find applications on Earth. Weather satellites, GPS, satellite communications, and many other conveniences of modern life grew out of the space program. The techniques developed for detecting biosignatures on distant planets might someday be used for environmental monitoring on our own planet. The international cooperation required for big science projects builds relationships that can help address other global challenges. The inspiration provided by space exploration motivates young people to pursue education in science, technology, engineering, and mathematics. The benefits are diffuse and hard to quantify, but they are real. As we continue our drift through this cosmic story, let us return to TRAPPIST-1e and consider once more what might be there. The James Webb Space Telescope has shown us hints of an atmosphere containing carbon dioxide and possibly ozone. The ozone is intriguing because it suggests the presence of oxygen, which on Earth is primarily produced by life. But ozone can also be produced by non-biological processes, so the finding is not definitive. Scientists are debating what it means and planning further observations to clarify the situation. We are at an early stage in a long investigation. The story is just beginning. If we eventually confirm that life exists on TRAPPIST-1, it will change everything. It will tell us that life is not unique to Earth, that the processes that led to living things here also occur elsewhere, that we are not alone in the vast emptiness of space. These conclusions would have profound implications for how we understand ourselves and our place in the universe. They would reshape philosophy, religion, and culture. They would open new questions about the nature of life, the possibility of intelligence, and the future of humanity among the stars. The discovery would be celebrated as one of the greatest achievements in human history if we eventually determine that TRAPPIST 1e is lifeless. That too will be informative. It will tell us that being in the habitable zone is not sufficient for life, that other factors are required that we do not yet fully understand. It will prompt us to look at other targets, refine our search criteria, and develop better models of planetary habitability. It will be a disappointment, certainly, but not a failure. Science advances by learning what is not true as much as by learning what is true. Every negative result narrows the possibilities and points us toward better hypotheses. The search will continue. Either way, the TRAPPIST 1e discovery marks a turning point. We have moved from speculation to investigation, from wondering to measuring, from asking whether habitable planets exist to studying the atmospheres of specific habitable planets. This transition is historic. It represents a new phase in humanity's exploration of the cosmos. Whatever we find on TRAPPIST 1e, the fact that we can look at all is a triumph, a testament to human curiosity, ingenuity, and persistence, a reminder that we are capable of great things when we set our minds to them. The concept of a universal biology is sometimes discussed in astrobiology circles. Is there a set of principles that all life must follow, regardless of where it arises? Are there universal constraints imposed by physics and chemistry that channel the evolution of life towards certain solutions? On Earth, life uses carbon as its structural backbone, because carbon forms strong, flexible bonds with many other elements. Life uses water as its solvent, because water has unique properties that facilitate biochemical reactions. Life stores information in nucleic acids, because these molecules are stable enough to preserve information across generations, but flexible enough to allow mutation and evolution. Are these choices universal, or are they just the particular path that Earth life happened to take? Some scientists argue that carbon-based, water-dependent life is the only viable form. The properties of carbon and water are so perfectly suited for biochemistry that no alternative could work as well. Others argue that alternative biochemistries are possible, at least in principle. Silicon might substitute for carbon in some environments. Ammonia or methane might substitute for water. Exotic solvents like liquid hydrocarbons on Titan might host unfamiliar forms of life. We simply do not know. Earth is our only example of a living planet. With a sample size of 1, we cannot draw statistical conclusions about what is necessary and what is merely contingent. Finding life on TRAPPIST 1e or anywhere else would give us a second data point, a second example to compare and contrast. It would revolutionize our understanding of what life can be. The search for life is also a search for ourselves. When we look for living worlds, we are asking what it means to be alive. What distinguishes living matter from non-living matter? What makes Earth special, if anything? These questions have occupied philosophers and theologians for millennia. Science is now joining the conversation with its own methods and perspectives. The answers we find, whatever they turn out to be, will change how we think about ourselves. They will reshape our sense of identity and purpose. They will inform our ethics and our politics. Finding that we are not alone would be the most important discovery in human history. But even the search itself, regardless of outcome, is transforming how we understand our place in the cosmos. Let us now turn to the technical challenges of confirming or refuting the biological hypothesis for TRAPPIST 1e's atmosphere. The detection of biosignatures is one of the hardest problems in observational astronomy. The signals are faint, The backgrounds are noisy. The interpretations are ambiguous. Every step in the chain from observation to conclusion involves assumptions that might be wrong. Scientists have developed a framework for assessing biosignature claims that involves multiple levels of confidence. At the lowest level, we have detection. Have we actually measured the signal we think we measured? Is it above the noise threshold? Is it reproducible? At the next level, we have identification. What molecule is responsible for the signal? Are we sure it is ozone and not some other chemical with a similar spectral feature? Then we have interpretation. What processes could produce this molecule? Are there non-biological explanations? How plausible are they? Only after all these levels are addressed can we begin to claim evidence for life. The TRAPPIST-1e data currently sits at the early stages of this framework. The detection seems solid. Multiple transit observations have been combined to produce a clear signal. The identification is tentative. The spectral features are consistent with ozone, but could potentially be explained by other molecules. The interpretation is hotly debated. Non-biological processes could plausibly produce the observed signals, but no single non-biological model explains everything perfectly. We are in the exciting but uncertain phase where more data is needed, more modeling, more analysis, more debate. This is exactly where science should be when confronting a potentially revolutionary claim. Cautious but curious, skeptical but open-minded, demanding evidence but willing to be surprised. One key test will be whether the atmospheric composition remains stable over time or varies in ways that might indicate biological activity. A living biosphere would be expected to maintain its atmosphere in a steady state, continuously producing and consuming various gases. This steady state might shift slightly with seasons or other cycles, but it would remain within certain bounds. A non-living atmosphere, by contrast, might show different patterns. Volcanic outgassing might produce irregular bursts of certain gases. Photochemical reactions might show variations tied to the star's activity, rather than any planetary process. By monitoring TRAPPIST-1's atmosphere over months and years, we might be able to distinguish between these scenarios. Another test involves looking for multiple biosignatures, rather than just one. On Earth, the presence of both oxygen and methane in the atmosphere is considered a strong biosignature because these gases react with each other and should not coexist unless something is continuously producing them. Finding both oxygen and methane on another world would be much stronger evidence for life than finding either alone. The Webb observations have hints of ozone, which is related to oxygen, but the evidence for other potential biosignatures like methane is less clear. Future observations will need to clarify whether TRAPPIST-1e has the kind of chemical disequilibrium that would strongly suggest biological activity. The broader scientific community is approaching these questions with a mixture of excitement and rigor. This is appropriate. Major claims require major evidence. The history of astrobiology is littered with false alarms and retracted claims. The famous Mars meteorite ALH 804001, announced in 1996 as containing evidence of Martian life, turned out to have a more mundane explanation. The detection of phosphine in Venus's atmosphere, reported in 2020 as a possible biosignature, remains controversial and unconfirmed. These experiences have taught the astrobiology community to be cautious, to demand multiple lines of evidence, to consider alternative explanations thoroughly. The TRAPPIST-1e findings are being held to this high standard, as they should be. Let us delve deeper into the specifics of what makes the TRAPPIST-1e atmospheric data so intriguing. The Webb telescope observed the planet during multiple transits, those moments when TRAPPIST-1e passes directly between its star and our line of sight. During a transit, a small fraction of the starlight passes through the planet's atmosphere before reaching us. This atmospheric transit light carries the fingerprints of whatever molecules are present in that thin shell of gas surrounding the planet. By carefully analyzing the spectrum of this transit light and comparing it to the spectrum of the starlight alone, scientists can identify which molecules are present and estimate their abundances. The technique sounds straightforward, but in practice, it is extraordinarily challenging. The atmospheric signal is tiny, typically just a few parts per million of the total starlight. Imagine trying to detect a single drop of dye in a swimming pool by looking at the color of the water from a great distance. Now imagine that the swimming pool is flickering and pulsing with its own internal variations. Now imagine that you are looking at it through a constantly shifting atmosphere that adds its own distortions. That is roughly the challenge facing exoplanet spectroscopists. Every data point is hard won. Every detection represents a triumph of instrumentation and analysis. For TRAPPIST-1e specifically, the Webb telescope used its near-infrared spectrograph, or NIRSpec, to observe multiple transits. NIRSpec can split incoming light into its component wavelengths with exquisite precision, allowing scientists to see the absorption signatures of different molecules. The team combined data from several transit observations to build up signal and beat down noise. The resulting spectrum showed clear evidence of carbon dioxide absorption at around 15 micrometers wavelength. This was the first unambiguous detection of any atmospheric molecule on a potentially habitable exoplanet. It confirmed that TRAPPIST-1e has an atmosphere, answering one of the biggest questions about the TRAPPIST-1 system. But the carbon dioxide detection was just the beginning. The team also noticed hints of other spectral features that did not fit a pure carbon dioxide atmosphere. One feature, at around 10 micrometers, was consistent with ozone absorption. Ozone is a molecule made of 3 oxygen atoms bonded together. On Earth, ozone forms when ultraviolet light from the sun breaks apart oxygen molecules, and the resulting free oxygen atoms combine with intact oxygen molecules to create ozone. This is why we have an ozone layer in our upper atmosphere. It shields us from harmful ultraviolet radiation. But ozone requires free oxygen to form, and free oxygen, on Earth at least, is produced almost entirely by photosynthetic life. This is what makes the ozone hint on TRAPPIST-1e so tantalizing. If the ozone is real, and if it requires oxygen to form, then where is the oxygen coming from? One possibility is photolysis of water vapor. Ultraviolet light can break apart water molecules into hydrogen and oxygen. The hydrogen, being light, can escape into space, while the heavier oxygen remains behind. Over billions of years, this process could build up significant amounts of oxygen in a planet's atmosphere without any biological involvement. This is called the runaway greenhouse scenario for oxygen accumulation, and it might explain oxygen on some exoplanets. But there are problems with applying this explanation to TRAPPIST-1e. The planet is not obviously in a runaway greenhouse state. Its estimated temperature is compatible with liquid water at the surface, not boiling steam. The amount of ozone hinted at in the data seems inconsistent with simple photolysis models. Something else might be going on, something that current models do not adequately explain. And when current models fail to explain an observation, that is when scientists get really interested. The research team has proposed several hypotheses to explain the ozone hint. The first is that it is a statistical fluctuation. The signal is weak enough that it might simply be noise masquerading as a detection. More observations will help clarify this. If the ozone signal persists and strengthens with additional data, it becomes more credible. If it fades or shifts, it was probably just noise. This is the null hypothesis, and it must be ruled out before more exotic explanations are considered. The second hypothesis involves volcanic outgassing. Volcanoes on Earth release various gases, including sulfur dioxide, carbon dioxide, and water vapor. Some of these gases can interact with ultraviolet light to produce ozone-like spectral features. If TRAPPIST-EU is volcanically active, and the tidal heating from its neighboring planets suggests it might be, then volcanic gases could potentially explain the observations. This would be interesting in its own right. It would tell us that the planet has a hot interior and active geology. But it would not require life. The third hypothesis is the biological one. Photosynthetic organisms on TRAPPIST-1e might be producing oxygen as a metabolic byproduct, just as plants and cyanobacteria do on Earth. This oxygen would react with ultraviolet light to form ozone, creating the spectral signature Webb might have detected. This is the most exciting hypothesis, but also the hardest to prove. We would need to rule out all non-biological explanations before concluding that life is responsible. The scientific process for distinguishing between these hypotheses will take years. More transit observations will refine the spectral data. Theoretical models will be developed and tested. Laboratory experiments will explore the chemistry of planetary atmospheres under TRAPPIST-1e's conditions. Computer simulations will predict what different scenarios should look like, and these predictions will be compared with observations. Slowly, painstakingly, the community will converge on a consensus. This is how science works, not through sudden revelations, but through gradual accumulation of evidence and patient refinement of understanding. While this work proceeds, other teams are studying other aspects of the TRAPPIST-1 system. One team is measuring the masses and densities of the 7 planets with increasing precision. These measurements tell us about the planet's compositions. Are they made mostly of rock, like Earth? Do they have large iron cores? Do they retain substantial amounts of water or ice? The answers inform our understanding of how the planets formed and what conditions might exist on their surfaces. TRAPPIST-1e appears to have a density similar to Earth's, suggesting a rocky composition. This is consistent with it being a potentially habitable world. Another team is studying the star itself. TRAPPIST-1 is a variable star, flickering and flaring as hotspots rotate across its surface and magnetic activity drives sudden outbursts. Understanding this stellar behavior is crucial for interpreting the planetary data. The star's flares could affect the planet's atmospheres, stripping away gases or creating chemical reactions. The star's variability could introduce noise into the transit observations, making it harder to detect faint atmospheric signals. By monitoring the star continuously, scientists can correct for some of these effects and extract cleaner planetary data. The question of whether TRAPPIST-1e has a magnetic field is particularly important. A magnetic field would help protect the planet's atmosphere from the stellar wind, the stream of charged particles constantly flowing outward from the star. Without magnetic protection, the stellar wind could gradually strip away atmospheric gases, leaving the planet bare. Earth has a strong magnetic field, generated by currents in our planet's liquid iron core. This field creates the Van Allen belts and the auroras, and it keeps our atmosphere firmly attached to our world. We do not know if TRAPPIST-1e has a similar field, but the fact that it has retained an atmosphere despite orbiting an active red dwarf suggests that some protective mechanism might be operating. The possibility of life on TRAPPIST-1e has also sparked interest in what kind of life it might be. On Earth, the first life appeared relatively quickly after the planet became habitable within the first billion years of Earth's history. But complex multicellular life took much longer to evolve, appearing only in the last half-billion years or so. If life on TRAPPIST-1e followed a similar timeline, and if the planet is roughly as old as Earth, then any life there might still be microbial. Single cells or colonies of cells invisible to the naked eye. Not the aliens of science fiction, but the aliens of microbiology. Still extraordinary, still revolutionary, but not the kind of life that could build civilizations or send signals into space. Of course, we cannot assume that life elsewhere would follow the same evolutionary timeline as life on Earth. Evolution is contingent. It depends on random events, environmental pressures, and chance encounters. Life on TRAPPIST-1e might have evolved faster or slower than life on Earth. It might have taken entirely different paths. It might have developed capabilities that Earth life never did, or it might be missing capabilities that we take for granted. We simply cannot predict what alien life would look like based on our single example of life on Earth. This is both frustrating and exciting. Frustrating because we cannot make confident predictions. Exciting because whatever we find will almost certainly surprise us. The detection of biosignatures is complicated by the fact that we do not know what alien biosignatures would look like. On Earth, life produces a distinctive set of gases and chemical compounds: oxygen, methane, nitrous, oxide, dimethyl sulfide, and many others. We look for these specific molecules because we know that Earth life produces them. But alien life might have a completely different metabolism. It might produce gases that we are not looking for. It might consume gases that we consider potential biosignatures. Without knowing what alien life is made of and how it works, we might detect it and not recognize what we are seeing. This problem has led some researchers to propose a more general approach to biosignature detection. Instead of looking for specific molecules, we should look for chemical disequilibrium. Life, by its nature, maintains chemical conditions that would not exist without it. On Earth, the presence of both oxygen and methane in our atmosphere is a disequilibrium signature. These gases react with each other and should not coexist unless something is continuously producing them. A world in chemical equilibrium would not have both. Finding such disequilibrium on another world, even if we do not recognize the specific molecules involved, would suggest that something is actively maintaining it, that something could be life. The TRAPPIST-1e data shows hints of chemical disequilibrium, which is part of what makes it so interesting. The combination of carbon dioxide and possible ozone is not what we would expect from a dead planet in photochemical equilibrium. Something seems to be maintaining conditions that would otherwise decay. This could be geological activity, volcanic outgassing balanced by atmospheric loss, or it could be biological activity, life producing and consuming gases in a dynamic balance. More data will help distinguish between these possibilities. The role of water in the search for life cannot be overstated. Water is the medium in which Earth's biochemistry operates. All known life requires liquid water at some point in its life cycle. The habitable zone around a star is defined as the region where liquid water could exist on a planet's surface. TRAPPIST-1e sits squarely in its star's habitable zone, but we do not know if it actually has liquid water. The presence of carbon dioxide in its atmosphere suggests that it might be too warm for surface ice, but cool enough to avoid a runaway greenhouse. Water vapor hints in the Webb data are consistent with water being present, but are not definitive. Future observations will hopefully clarify the situation. If TRAPPIST-1e has liquid water, the question becomes where that water is located. On a tidally locked planet, water on the day side would tend to evaporate and be transported to the night side by atmospheric circulation. This could lead to a situation where the night side is covered in ice while the day side is dry. The habitable region would then be limited to the terminator zone, the boundary between day and night, where temperatures might allow liquid water to persist. Alternatively, if the planet has oceans, the water's thermal inertia might help distribute heat more evenly around the planet, creating a more uniformly habitable environment. The details depend on many factors we do not yet know, including the planet's topography, atmospheric thickness, and heat transport efficiency. The search for water on TRAPPIST-1e connects to the broader search for water throughout the universe. Water is not rare. It is one of the most common molecules in space. Comets are made largely of water ice. The moons of Jupiter and Saturn have subsurface oceans. Mars once had liquid water on its surface and still has water ice at its poles. The building blocks of water, hydrogen, and oxygen are among the most abundant elements in the cosmos. If life requires liquid water, as Earth life does, then the prevalence of water throughout the universe suggests that the conditions for life might also be prevalent. The implications extend beyond TRAPPIST-1e to the galaxy as a whole. If life exists on TRAPPIST-1e, it suggests that life can arise on planets orbiting red dwarf stars. Red dwarfs are by far the most common type of star in the galaxy, making up about 75% of all stars. They are also extremely long-lived, burning steadily for trillions of years. If red dwarf planets can host life, then the majority of habitable planets in the galaxy would be orbiting red dwarfs. The total number of living worlds could be vastly higher than estimates based on sun-like stars alone. This has implications for the Fermi paradox we discussed earlier. If life is common around red dwarfs, and if red dwarfs are the most common stars, then life should be extremely widespread throughout the galaxy. The question of why we have not detected any signs of other civilizations becomes even more pressing. Either intelligent life does not arise often from simpler life, or intelligent civilizations do not last long, or they choose not to make themselves visible, or we are simply not looking in the right way. The TRAPPIST-1 discovery does not resolve the paradox, but it sharpens it. At the same time, there is a recognition that we might be approaching a genuine breakthrough. The combination of better telescopes, better techniques, and promising targets has brought us closer to answering the question of extraterrestrial life than ever before. Some scientists believe that the first convincing evidence of life beyond Earth will come within the next decade or two. Others are more conservative, expecting that confirmation will take longer. But almost everyone agrees that we are living in a special time, a time when the ancient question might finally receive a scientific answer, a time when our cosmic loneliness might come to an end. The rate of technological progress in astronomy has been staggering over the past few decades. When the Hubble Space Telescope launched in 1990, we did not know of a single planet outside our solar system. Today, we know of thousands, and we are characterizing the atmospheres of the most interesting ones. The James Webb Space Telescope, launched in 2021, is already rewriting our understanding of exoplanets. In another 30 years, we will have instruments that make Webb look primitive. The pace of discovery is accelerating, and the questions we can ask are becoming ever more profound. Consider what we have accomplished in just one human lifetime. A person born in 1950 would have grown up in a world where the existence of exoplanets was purely speculative. By the time they reached middle age in the 1990s, the first exoplanets were being discovered. By their retirement years in the 2020s, thousands of exoplanets were known, and scientists were debating whether one of them might harbor life. This is an extraordinary arc of discovery, and the person who witnessed all of this might live to see the question of extraterrestrial life definitively answered. That would be a journey from speculation to knowledge spanning a single human lifespan. The emotional weight of this potential discovery should not be underestimated. For many people, the question of whether we are alone in the universe is deeply personal. It touches on their sense of meaning and purpose. It connects to their religious beliefs or philosophical worldview. It speaks to their feelings of cosmic loneliness or cosmic belonging. Finding life elsewhere would not just be a scientific achievement. It would be a transformation in how humanity understands itself. A new chapter in the story we tell about who we are and where we come from and where we might be going. Different people would react to such a discovery in different ways. Some would celebrate. They would see it as confirmation that the universe is alive, that we are part of a larger community of beings, that our existence is not a cosmic accident, but part of a natural process that occurs throughout the galaxy. Others might feel threatened. Their beliefs about human uniqueness and special creation might be challenged. They might worry about the implications for religion or philosophy or politics. Still others might simply shrug and go about their daily lives. Not everyone cares about cosmic questions. For some people, the problems of everyday existence are more than enough to occupy their attention. The scientific community would react with a mixture of excitement and caution. Extraordinary claims require extraordinary evidence, and the bar for accepting a claim of extraterrestrial life would be set very high. Independent verification would be essential. Multiple lines of evidence would be demanded. Alternative explanations would be thoroughly explored. Only after surviving this intense scrutiny would a claim of life beyond Earth be accepted by the scientific community as a whole. This process would take time, years, perhaps decades. But if the evidence held up, the eventual acceptance would be all the more credible for having passed such rigorous testing. The TRAPPIST-1 discovery is not yet at the stage where we can claim evidence of life. We have hints, we have anomalies, we have observations that are difficult to explain with known non-biological processes, but we do not have proof. The work of gathering that proof, or of ruling it out, will occupy scientists for years to come. Each new observation will add to our understanding. Each theoretical advance will refine our interpretations. Slowly, the picture will come into focus. We will learn what is really happening on that small rocky world, orbiting its small red star 40 light years away. In the meantime, we can appreciate the journey. The search for life beyond Earth is not just about the destination. It is about the process of searching, the questions we ask, the methods we develop, the teamwork and cooperation required. The wonder and excitement we feel along the way. Even if TRAPPIST-1 turns out to be lifeless, the search will have been worthwhile. We will have learned something about the universe. We will have pushed the boundaries of human knowledge. We will have done what humans do best, explored the unknown, asked difficult questions, and sought answers with courage and curiosity. The universe is vast and ancient and largely indifferent to human concerns, but it is also beautiful and strange and full of wonders. The fact that we exist at all is remarkable. The fact that we can ask questions about our existence is more remarkable still. And the fact that we are developing the tools to answer those questions is perhaps the most remarkable thing of all. We are small creatures on a small planet, but we have big dreams. We want to know if we are alone. We want to know if life is common or rare. We want to know what other forms consciousness might take and what other worlds might exist. These are the questions that drive the search for life beyond Earth, and they are questions that make us human. The story of TRAPPIST-1e is ultimately a story about human curiosity and ingenuity, about our drive to understand the universe and our place in it, about our refusal to accept ignorance when knowledge is possible. We built the most powerful telescope ever launched because we wanted to see what was out there. We pointed it at a tiny star 40 light-years away because we thought its planets might be interesting. We analyzed the light that filtered through an alien atmosphere because we hoped to find something extraordinary. And we found hints, just hints for now, but hints that point toward possibilities that would have seemed like fantasy just a generation ago. As we approach the climax of our journey, let us gather what we have learned. The James Webb Space Telescope has detected an atmosphere on TRAPPIST-1e, one of the most promising, potentially habitable exoplanets known. The atmosphere contains carbon dioxide and possibly ozone and water vapor. The presence of ozone is particularly intriguing because on Earth, ozone is produced as a byproduct of oxygen, and oxygen is produced primarily by photosynthetic life, while non-biological processes can also produce ozone. The specific characteristics of TRAPPIST-1e's atmosphere are difficult to explain without invoking unusual geological or potentially biological activity. Scientists are debating the implications and planning future observations to clarify the situation. We are closer than ever before to answering the question of whether life exists beyond Earth. But the significance of this discovery goes beyond the specific chemicals detected in one atmosphere. It represents a shift in how we think about the search for life. For decades, the search was mostly speculative. We knew that habitable planets probably existed, but we could not study them directly. We could theorize about what alien life might look like, but we had no data to constrain our theories. Now we have data, imperfect data, ambiguous data, but data nonetheless. We can test our theories against reality. We can refine our models based on actual observations. We can make predictions and check whether they come true. This is how science progresses, through the interplay of theory and observation, through the gradual accumulation of evidence, through the patient work of many researchers over many years. The TRAPPIST-1e findings also illustrate the power of international scientific collaboration. The Webb Telescope is a joint project of NASA, the European Space Agency, and the Canadian Space Agency. Researchers from dozens of countries have contributed to the design, construction, and operation of the instrument. The data it collects is shared with the global scientific community. Papers analyzing that data are authored by teams spanning continents. Science at its best is a cooperative endeavor, a pooling of resources and talents toward common goals. The search for life beyond Earth is perhaps the most universal of these goals. It transcends national boundaries and political divisions. It unites humanity in a shared quest for understanding. And yet, the search is also intensely personal. Every scientist involved has their own reasons for caring about this work, their own hopes and dreams, their own moments of excitement and frustration. Behind the papers and the press conferences are human beings grappling with big questions. Is there life out there? Are we alone? What does it mean if we find something? What does it mean if we do not? These questions touch on our deepest existential concerns. They connect to our sense of meaning and purpose. They resonate with our wonder and our fear. The search for life is not just an intellectual exercise. It is a spiritual one, in the broadest sense of that word. As we drift toward the conclusion of our journey, let us consider what comes next. The Webb telescope will continue to observe TRAPPIST-1e and other promising exoplanets. Each observation will add to our understanding. Each data point will narrow the possibilities. Over the coming months and years, we will learn more about what is happening on this distant world. We will either confirm the hints of biological activity or find alternative explanations that dispel them. Either outcome will be valuable. Either outcome will teach us something important about how planets work and how life arises. But before we conclude, let us explore some of the deeper philosophical implications of what we have discussed. The search for life beyond Earth is not just a scientific endeavor. It is also a profound meditation on what it means to be alive, to be conscious, to be part of a universe that can wonder about itself. These questions have occupied human minds for as long as we have had the capacity to ask them. Now, for the first time, we have the tools to seek empirical answers. Consider the sheer improbability of our existence. The universe is roughly 14 billion years old. For most of that time, there was no life anywhere, at least as far as we know. Stars formed and died. Galaxies collided and merged. Heavy elements were forged in stellar cores and scattered into space by supernova explosions. Slowly, over billions of years, the raw materials for life accumulated. Then, on at least one small rocky planet orbiting an unremarkable star in an average galaxy, something remarkable happened. Chemistry became biology, dead matter became alive, and eventually, that life became aware of itself and began to ask questions about its origins. How did this happen? What are the conditions necessary for the emergence of life? Is life an inevitable consequence of certain physical and chemical conditions? Or is it a rare accident that requires an extraordinarily unlikely sequence of events? These are the questions that the search for extraterrestrial life seeks to answer. If we find life on TRAPPIST-1e or any other world, we will know that life can arise independently in multiple places. This would suggest that life is not a cosmic fluke, but a natural tendency of matter under the right conditions. It would mean that the universe is, in some sense, fertile, designed, if not by an intelligence, then by the laws of physics themselves, to produce living things. Alternatively, if we search extensively and find no life anywhere else, we will know that Earth is somehow special, that the conditions required for life are extraordinarily rare, that we are, perhaps, alone in a universe that is vast and old and mostly empty. This would be a sobering conclusion, but it would also be profound in its own way. It would mean that everything we value about life, consciousness, creativity, love, and meaning exist nowhere else. It would make Earth infinitely precious, a singular oasis of warmth and light in an otherwise cold and dark cosmos. The philosopher Blaise Pascal wrote about the terror of infinite spaces, the realization that the universe is immensely larger than we are and utterly indifferent to our existence. This cosmic anxiety is real. Many people feel it when they contemplate the scale of the universe and their own smallness within it. Finding life elsewhere might actually help with this anxiety. It would mean that we are not alone in facing the void, that other beings on other worlds share our situation, that the universe, for all its vastness, is not completely empty of companions. There would be others out there, looking up at their own skies, wondering the same things we wonder. The cosmic loneliness would be eased, but finding life might also raise new anxieties. If life is common, why have we not heard from anyone? This is the famous Fermi paradox. named after the physicist Enrico Fermi, who reportedly asked this question over lunch one day in the 1950s. If the galaxy is old enough and large enough for many civilizations to have arisen, why is there no evidence of their existence, no radio signals, no megastructures visible to our telescopes, no visits from alien spacecraft? The silence is puzzling. Various explanations have been proposed. Maybe civilizations destroy themselves before they can spread across the stars. Maybe they choose to remain hidden. Maybe the distances are simply too great for meaningful contact. Maybe we are just not looking in the right way. The Fermi paradox remains unsolved, and finding microbial life on TRAPPIST 1 would only make it more pressing. The Drake equation, which we mentioned earlier, attempts to quantify the factors that determine how many civilizations might exist in our galaxy. Most of these factors are unknown, so estimates vary wildly, from 0 to millions. The discovery of life on TRAPPIST 1 would help constrain some of these factors. It would tell us that the fraction of habitable planets where life actually arises is not 0. This would shift our estimates upward, making it more likely that other civilizations exist or have existed. But it would not tell us about the other factors in the equation. How often does life become intelligent? How often does intelligence develop technology? How long do technological civilizations last? These questions remain open. Some thinkers have proposed that we might be among the first civilizations in the galaxy. The universe is about 14 billion years old, but the heavy elements necessary for rocky planets and complex chemistry were not abundant until several billion years after the Big Bang. Earth is about 4.5 billion years old, and it took most of that time for intelligent life to evolve here. Perhaps we are near the beginning of the era when intelligent life can exist. Perhaps most civilizations that will ever arise have not yet emerged. In this view, the silence of the cosmos is not mysterious. It simply reflects the fact that there is no one else yet to make noise. We are the first comers, looking out at an empty galaxy that will eventually be filled with life. Others have proposed that civilizations tend to destroy themselves shortly after developing advanced technology. Nuclear weapons, artificial intelligence, climate change, and pandemics all pose existential risks to humanity. Perhaps these risks are universal. Perhaps every civilization that reaches a certain level of technological sophistication faces the same challenges, and most fail to navigate them successfully. In this view, the silence of the cosmos is a warning. It tells us that the road we are traveling has a cliff at the end, that intelligence, left unchecked, tends towards self-destruction. This is a disturbing possibility, but it would be valuable information if true. It would give us a reason to be more careful, more thoughtful, more intentional about how we develop and deploy our technologies. Still others have proposed that advanced civilizations deliberately hide themselves from younger civilizations like ours. Perhaps there is a cosmic community of intelligent beings who have decided, for whatever reason, not to reveal themselves to newcomers. Perhaps they are waiting for us to reach a certain level of maturity before making contact. Perhaps they are observing us, studying us, deciding whether we are worthy of membership in their community. This is the zoo hypothesis, the idea that we are being watched but not contacted, like animals in a nature preserve. It is impossible to prove or disprove, but it captures a certain imaginative appeal. Who would not want to believe that there are wise elders out there waiting to welcome us when we are ready? The search for life on TRAPPIST 1 is part of this larger conversation. It is one thread in a tapestry of questions about our place in the cosmos. The discovery, whatever it turns out to be, will add to our understanding and refine our thinking. It will not answer all the questions, but it will help us ask better ones. And that ultimately is what science is about. Not final answers, but better questions. Not certainty, but progressive reduction of uncertainty. Not the end of inquiry, but its continuation at a higher level of sophistication. Let us also consider the ethical implications of finding life elsewhere. If there are microbes on TRAPPIST-1e, do we have moral obligations toward them? This might seem like a strange question. We do not typically think of microbes as having moral status. We kill billions of them every time we wash our hands. But alien microbes would be different. They would represent an entirely independent origin of life, a separate branch on the tree of existence. They would be, in a sense, infinitely precious, the only other example of life we know of in the entire universe. Do we have an obligation to protect them, to study them without contaminating or harming them, to respect their existence even if they are not aware of us? These questions are not merely theoretical. If we ever send probes to other worlds that might harbor life, we will face them directly. Current planetary protection protocols are designed to prevent Earth life from contaminating other worlds and potentially destroying any native life before we have a chance to study it. But these protocols are based on practical concerns about scientific integrity, not ethical concerns about the rights of alien microbes. As our capabilities grow, and as the possibility of extraterrestrial life becomes more concrete, we may need to develop a more robust ethical framework for our interactions with other living systems. Similar questions arise about intelligent life, if it exists. If there are beings on other worlds who are capable of thought and feeling, do we have moral obligations toward them? Do they have rights? Can we interact with them without causing harm? These questions have been explored in science fiction, but they may eventually need to be addressed in science fact. The search for extraterrestrial intelligence is not just about satisfying our curiosity. It is about preparing ourselves for a universe that may be full of minds other than our own. The TRAPPIST-1e discovery also has implications for our understanding of Earth and its future. If life can arise and persist on a world like TRAPPIST-1e, with its challenging environment and its angry parent star, then life on Earth may be more resilient than we thought. Our own sun will eventually expand into a red giant, boiling away the oceans and scorching the surface. Life on Earth, in its current form, will not survive. But perhaps life in some form could persist even then. Perhaps extremophiles living deep underground could continue for billions of years after the surface becomes uninhabitable. Perhaps life could migrate to the outer solar system, to the moons of Jupiter and Saturn, as the sun's habitable zone expands outward. The resilience of life on TRAPPIST-1e would give us reason to hope that life on Earth might have a longer future than we typically assume. Conversely, if TRAPPIST-1e turns out to be lifeless despite being in the habitable zone, it would remind us how special Earth's conditions are. Our magnetic field, our thick atmosphere, our large moon, our plate tectonics, our distance from the galactic center, and countless other factors have combined to make Earth hospitable to life for 4 billion years. Change any of these factors, and life might not have emerged or might not have persisted. We should not take our existence for granted. We should protect and preserve the conditions that make life possible here, even as we search for life elsewhere. The story of TRAPPIST-1e is also a story about the power of human cooperation. The James Webb Space Telescope was built by thousands of people from dozens of countries working together toward a common goal. The observations of the TRAPPIST-1 system involved astronomers from around the world, sharing data and ideas across national boundaries. The papers published about the findings have authors from multiple institutions and countries. Science, at its best, is a global endeavor. It transcends the divisions that often separate us. It reminds us that we are all human beings living on the same small planet, trying to understand the same vast universe. This spirit of cooperation will be essential as we continue to explore the cosmos. The challenges are too great for any one nation to tackle alone. The questions are too important to be monopolized by any one group. The answers, when we find them, will belong to all of humanity. The search for life beyond Earth is perhaps the most unifying scientific project ever undertaken. It asks a question that people of all cultures, religions, and backgrounds can understand and care about. Are we alone? The answer, whatever it turns out to be, will be an answer for all of us. As we approach the final moments of our journey tonight, let us return to the image we began with. A small rocky planet, 40 light-years away, orbiting a small red star. A world that might, just might, be home to living things. We cannot see it directly. It is too far away, too dim, too obscured by the glare of its parent star. But we can detect its presence. We can analyze the light that filters through its atmosphere. We can read the chemical fingerprints that tell us about the conditions on its surface. And from those faint signals, we can begin to imagine what it might be like. What creatures might walk its twilight shores? What thoughts might stir in minds we have not yet discovered? This is the remarkable gift of science. It extends our senses beyond their natural limits. It allows us to see things that are invisible to the naked eye, to hear things that are inaudible to the unaided ear, to know things that our ancestors could never have known. The James Webb Space Telescope is an extension of human vision, a golden eye gazing into the depths of space and time. Through it, we can see the universe as it was billions of years ago. We can peer into the hearts of stars and the atmospheres of distant worlds. We can search for signs of life across the cosmic ocean, and we can do all this while sitting in our homes, listening to a gentle voice, drifting peacefully into dreams. The universe is vast beyond comprehension. Hundreds of billions of galaxies, each containing hundreds of billions of stars, spread across a void that has been expanding for 14 billion years. In all that immensity, we know of only one place where life exists, this small blue dot, spinning around a medium-sized star, in an unremarkable corner of an average galaxy. But perhaps 40 light-years away, there is another place, another world where matter has organized itself into patterns that can grow and reproduce and evolve. Another expression of the cosmic tendency toward complexity and wonder. The thought is humbling and exhilarating at the same time. Whether or not life exists on TRAPPIST, the search itself is valuable. It pushes the boundaries of what we know. It inspires us to ask big questions and seek big answers. It reminds us of our place in the cosmos and our connection to everything that exists. The search for life is, in the end, a search for meaning, a search for our place in the grand story of the universe. And even if we never find what we are looking for, the searching itself makes us more fully human. Beyond Webb, new instruments are on the horizon. The extremely large telescopes being built in Chile and Hawaii will have unprecedented resolution and sensitivity. They will be able to study exoplanet atmospheres in ways that are impossible today. The Nancy Grace Roman Space Telescope will survey the sky for planets and provide context for the targets we study in detail. Future missions to Europa and Enceladus will search for life in our own solar system. The next few decades promise to be extraordinarily exciting for astrobiology. We are entering a golden age of discovery. The question of whether life exists on TRAPPIST-1e remains open. But the fact that we can ask this question seriously, based on real data rather than speculation, is itself remarkable. A generation ago, we did not know if any planets existed outside our solar system. Now we know of thousands, and we are analyzing the atmospheres of the most promising ones. The rate of progress has been extraordinary. If this pace continues, and there is every reason to expect it will, the question of extraterrestrial life may be answered within our lifetimes. That is a stunning thought. We might be the generation that discovers we are not alone. But whether or not life exists on TRAPPIST-1e, the search itself has value. It pushes us to develop new technologies. It inspires young people to pursue careers in science and engineering. It encourages international cooperation. It reminds us of what humanity can achieve when we work together toward a common goal. The search for life is not just about finding life. It is about expressing the best of what we are. Curious creatures on a small planet, reaching out toward the stars, hoping to find companions in the cosmic dark. And so we come to the resolution of our story, though not yet its end. The James Webb Space Telescope has shown us something unexpected on TRAPPIST-1e, something that challenges our assumptions, something that opens new possibilities. Whether this something turns out to be life or something else entirely, we've learned that the universe continues to surprise us, that our models are incomplete, that reality is richer than our theories. This is the eternal lesson of science. Humility before nature, openness to surprise, the willingness to be wrong in pursuit of being less wrong. If there is life on TRAPPIST-1e, it has survived for billions of years in an environment we would consider hostile, bathed in flares from an angry star, tidally locked in eternal day and eternal night, subject to atmospheric loss that would strip away the air from less fortunate worlds. Yet life persisted. Life found a way. This would tell us something profound about the resilience of living systems, about the determination of life to continue existing once it gets started, about the stubbornness of biology in the face of physical adversity. Life on Earth has survived asteroid impacts and ice ages and mass extinctions. Life on TRAPPIST-1e might have survived stellar tantrums and atmospheric erosion. Life, it seems, is hard to kill once it takes hold. If there is no life on TRAPPIST-1e, that too would be informative. It would tell us that being in the habitable zone is not enough, that other factors matter too. Perhaps magnetic fields are essential. Perhaps plate tectonics are required to cycle nutrients. Perhaps large moons are necessary to stabilize planetary rotation. We would learn about the filters that prevent life from arising on otherwise promising worlds. We would refine our estimates of how common life is in the galaxy. We would focus our future searches on targets that pass these additional tests. Every answer opens new questions. Every discovery points toward new mysteries. This is the nature of exploration. The universe is under no obligation to be comprehensible, as Einstein once noted. But it has turned out to be surprisingly so. The laws of physics that govern our world also govern the stars. The chemistry that enables life on Earth might enable life elsewhere. The curiosity that drives us to explore is itself a product of cosmic evolution. We are the universe trying to understand itself. Stardust contemplating starlight. Matter pondering matter. In searching for life beyond Earth, we are continuing a journey that began when the first human looked up at the night sky and wondered what was out there. That journey will never end. Even if we find life on 1,000 worlds, there will always be more to discover. More worlds to explore, more questions to answer, more mysteries to unravel. The search for life is not a project with a finish line. It is an ongoing adventure, a way of being in the world, a stance toward reality that combines wonder and rigor, hope and skepticism, ambition and humility. It is, in short, what makes us human. And that wraps up today's cosmic journey to TRAPPIST 1e. What an incredible time to be alive, right? We are witnessing humanity reach out across the void and touch, however lightly, the shores of alien worlds. The James Webb Space Telescope has given us a glimpse of something extraordinary, something that might shift the entire discussion about where life can exist and what forms it might take. If you enjoyed this peaceful drift through space and discovery, please consider hitting that like button. It really helps the channel grow and brings more cosmic stories your way. And if you have not already, please subscribe so you do not miss our next journey through the universe. We would love to hear from you. Drop a comment below and let us know what you think about TRAPPIST 1e and the possibility of life beyond Earth. Where are you watching from tonight? Are you drifting off under the stars or settling into your cozy corner of the cosmos? Thank you so much for joining us here at Cosmic Drift. As you close your eyes and let the wonders of the universe carry you gently into dreams, remember that somewhere out there, 40 light years away, a small world orbits a small star, and on that world, something might be looking up at its own sky, wondering about us. Sweet dreams, fellow cosmic travelers. We will see you in the next one.